In this unit, we're going to be talking about system stability. So if you recall back to our very first unit, we said there were three important items that we want to consider when we're designing a system. The first one was our transient response. And so our transient response is what we've been looking at in the past couple units, well really the past 3 units. So we sort of started by saying, how do we model these systems? Once we had that, we said, here's how we can do our time response, which is really, we were focusing on the transient response aspect of that. And then in the last unit, we were looking at how do we rearrange or reduce our systems so we can get a better idea of what the transient response is for complicated systems. So we've already taken a look at our transient response. Our second key item is what we're going to look at now, which is our stability. And our third key item, which we're going to take a look at in our next unit, is our steady state response. Sorry, our steady state errors. So the errors in our steady state response. And so of these 3 items, this stability is going to be our most important. And so the reason this is our most important is, of course, in a lot of cases, for instance, in our elevator example, if our system isn't stable, then that's going to be a big safety concern. So for example, if we were to push a button and tell our elevator to go to floor number 4, and instead the elevator crashes out the ceiling of the building, obviously that's not even remotely desirable. So our stability of systems is very important. So before we talk about our systems explicitly and we relate everything back to our poles and we analyze how to figure out if a system's stable or not, let's start by looking at some definitions for stability. So definitions of stability. So there's a couple different ways that we can define stability. One way that we can talk about defining stability is something called bounded input, bounded output. So bounded input, bounded output. Let's see if I can spell right. There we go. And so sometimes we'll just abbreviate this BIBO. And so what this is basically if we have some system that has a bounded output for every bounded input, we say the system is stable. So our system would be stable if every single bounded input results in a bounded output. Now, what do I mean when I'm talking about bounded inputs, bounded outputs? So if we think about a signal over time, an unbounded signal would be one that is growing sort of not necessarily exponentially, but it continues growing over time and it never really has any sort of limit. So we're saying we're putting in bounded inputs, so that's not the case for our input. And if we have every bounded input corresponds to a bounded output, then our system is going to be stable. The idea being that we're not going to intentionally put some unbounded input into the system. So if our system is unstable, that would be sort of the opposite case of for bounded inputs, for some of them, we're getting unbounded output. So our system is going to be unstable if there exists any bounded input that results in an unbounded output. So bounded input results in unbounded output. And then we sort of have this case in between, which we could say a system can be marginally stable. And so this is sort of on that knife edge between stability and instability. So our system would be marginally stable if some, but not all, bounded inputs create bounded outputs. Sorry, yes. So some, but not all bounded inputs create bounded outputs. And so I think that these definitions using our bounded input, bounded outputs can be a little bit confusing. So another way that we can define this is based on our natural response. And so I think that personally this way makes a little more sense to me, but I know that's not the case for everybody. So let's also define in terms of our natural response. And so recall that in general, if we have some output, which is a function of time, it's going to be the sum of our forced response and our natural response. So both of those are also functions of time. So we have c forced of time and c natural of time. And so what we're focusing on here is this natural part of this c of t. And we can say that for system stability, that c natural is going to go to 0 as t goes to infinity. So we'll say that our system is stable if our c natural is going to 0 as our t goes to infinity. And so that's sort of what I was explaining earlier in terms of our bounded input or bounded output. So basically we could say if the input or output is going to 0 as our t goes to infinity, we'd say that is a bounded input or a bounded output, or more generally a bounded signal. So in contrast to this, of course, we could say that a system is going to be unstable if that c natural is growing as t goes to infinity. So our system is going to be unstable if c natural grows without bounds as t goes to infinity. And so, of course, sort of a really general example of this is maybe we have some sinusoidal output, and so maybe here's sort of our median value, and so if that sinusoidal output over time just continues to grow, so that would be an unbounded output or an unbounded natural response. So we can also talk about, we have our stability and instability. We can also talk about sort of that transitional case between the two, which is marginal stability. So we can say our system is going to be marginally stable if our c natural is just remaining constant or oscillating. So system is marginally stable if our c natural is remaining constant or oscillating. And that's as t goes to infinity. So now, of course, we're going to want our system to be stable. We don't want it to be marginally stable because, of course, one little push in the wrong direction due to some disturbance, and we could then have an unstable system. So our target, of course, is always going to be system stability. So I know these sort of general definitions are a little difficult to sort of make sense of where we're going. So in the following videos, we're going to relate this to our actual transfer functions and our poles. And then after we do that, we're going to look at a method where we can analyze the system in a little more detail.